Welcome to a video on per unit quantities. Across all electrical grids, different segments are at different voltage levels. This means that performing analysis across a network is computationally tedious and prone to error, because for each segment we need to take into account its particular voltage level. To combat this issue, a system has been devised to simplify values across voltage, current, resistive, reactive and complex impedance, and real, reactive and apparent power. In this method, parameters are translated to a normalized quantity from their actual value, be it volts or amps, etc., with respect to a base value. We call this normalized quantity per unit quantity, as it represents a value as per a base unit. So the quantity in per unit is equal to the actual value divided by its base value. Think about what we're doing here. We're effectively absorbing large differences in these absolute values into base relationships. There are a couple of key advantages to this way of representing values. Firstly, quantities are normalized or dimensionless, meaning they have no units and can therefore be easily related to one another. Secondly, quantities are easy to check. This helps identify performance requirements, for example voltage ranges and impedance values, because these are normally specified as a percentage of the base value. Also, it facilitates sanity checks for erroneous values, because device parameters tend to fall in relatively fixed ranges. The last advantage is that ideal transformers are eliminated using this methodology. We'll get to that bit later. So how do we select this base quantity? Well, in the spirit of what the tool was designed for, we make things convenient for ourselves and set it as close to the standard value in a circuit as possible. So for a 10 volt circuit, I could set a base value to 10 volts, making my per unit voltage simply 10 volt divided by 10 volt, which is equal to unity. Note that this is a dimensionless quantity, meaning that it's just a ratio. It's just like saying 100%. But we just said we want to simplify across voltage and current and impedance and power. Now we only have to set a base quantity for voltage? Almost. It's best to visualize all these different parameters of a circuit as intrinsically linked in a sort of web. This dramatically simplifies the implementation of per unit representations. For example, we know that voltage and current are linked with impedance through Ohm's law, and that they're also linked through the power law to power. Because all the parameters are connected in some way, we can prove quite easily that if we were to set any two, let's say some arbitrary voltage value and some arbitrary apparent power value, we could get a corresponding unique value for each of the rest. What does this mean? For any power circuit, we need only to select a set voltage and a set apparent power, and we have defined the entirety of the base values for that circuit. So we now know there are 2 degrees of freedom when deciding what bases we want to set, and that the 2 standards selected are voltage and apparent power. Now we'll run through all the relationships between bases. It's important to note at this point that bases for each parameter have a single phase and 3-phase form. For voltage, we use line to neutral voltage as our single phase base, and line to line voltage as our 3-phase base. For apparent power, we use single phase power and 3-phase power respectively. Here are the current and impedance bases. Note that they are formed exclusively from the voltage and apparent power values, as we recently discussed. Note, the bases for the real and complex components of the complex power and complex impedance respectively all have the same base. There are 2 conventions that we follow when propagating these bases through any system. The first is that the value of the apparent power base is maintained throughout the system. The second is that the voltage base shifts across transformers in proportion with the number of turns in that transformer. So for a transformer with a 1 to 10 turn ratio, the base voltage on the secondary side will also be 10 times larger than the base voltage on the primary side. Why would we do this? Well, for an ideal transformer, this per unit system removes the need to convert voltages from one side to the other. So if the system is at nominal voltage, this will be represented on both sides as 1 per unit, and we can avoid concerning ourselves with turn ratios.
For a real transformer like the one shown here with some impedance either side, the per unit system again helps us by simplifying the transformation of impedance from one side to the other. So instead of doing tedious work of recalculating the impedances from one side into the other using N1 on N2 all squared, we preset the base value for that entire section to be at a different level so the transformer effectively disappears.
We are effectively encapsulating the impedance discrepancy in terms of a base voltage. The per unit impedance of a generator or transformer, as supplied by the manufacturer, is generally based on the rating of the generator or transformer itself, and therefore different from the base of the system into which it will be installed. So how do we go about resizing our per unit values to correspond to different bases? Say we have a per unit value 1, and we are trying to resize it to another per unit value 2. Recall that per unit values are just ratios of actual values to base values. In our case, we have the exact same actual value, just divided by a different base. Because of this equivalence, we can rearrange our equation, and then again to make it in terms of our first per unit value. Therefore, if we know what the previous per unit and base values were, as well as the base value of the per unit value we want, we can alter any per unit quantity. Here are the equations to move from any per unit value to another, using the relevant voltage and apparent power bases. We now have everything we need to attempt an example. Here's a generator connected to a motor across a transformer. We know that the voltage of the generator is 480 volts and the apparent power is 20 kilovolt amperes. Let's set these to be our base values, the voltage for this section and the power for the entire system. That leaves the voltage base in the second section unknown. We know that the voltages either side of a transformer are directly related to the number of turns in the primary and secondary windings, so we can set the voltage base for the second section to be 240 volts. Now let's say that we wanted to find the per unit impedance of this transformer. There's a quoted 10% impedance value here, but we can see that the base power is not the same as that of our unit. We therefore need to use an impedance equation from before to find the new per unit impedance value. Now what if we wanted to find the impedance of the transformer in ohms? Well, that depends on what side of the transformer we're observing from, as they have different voltage levels and thus different base impedances. You can see then that it's much less confusing and much more convenient to use a system of bases and per unit values over actual values.